Dear students, welcome to the lecture series on power system analysis. Today we will be discussing the topic steady state power transfer. So, for explaining the steady state power transfer and the factors that depend on this power transfer, we have taken an example. So here we have a three-phase system which is represented by a single end anchor. So this system is having a synchronous machine which is connected to the bus, and this bus is connected to the load via a transmission line. Sending end, and this is the receiving end. So the receiving end voltage is given by VR angle 0, and this voltage is taken as the reference and we have taken the angle 0, and sending end voltage is given by Vs and delta is the angular difference between the sending end voltage and the receiving end voltage, and it is connected through a transmission line with Z impedance, and IR is the current that is flowing through this transmission line, and the complex power that is transferred to the load is given by SR, which is equal to PR plus JQR. PR is the real part and QR is the imaginary part, the reactive power, and the load is assumed to be an asynchronous one. It can be synchronous also, and the complex power is given by SR equal to VR into IR conjugate. So this IR conjugate is an important concept that you need to understand. So IR is given by sending end voltage minus receiving end voltage divided by the impedance, okay, the whole conjugate. And you are using IR conjugate for a reason that we will explain towards the end of the lecture. So that is VR angle 0 into IR conjugate, the complex power. Now your complex power can be simplified when you take your theta minus 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 minus theta. It is delta theta. You will have theta minus delta once you remove the conjugate, and here it is minus theta, that becomes theta when you remove the conjugate. Now SR is given by Vs VR by Z angle theta minus delta minus VR squared by Z angle theta. Now if you neglect the value of resistance, you are assuming that your line is purely reactive, you will have theta equal to 90. So you will have real the power flow equation SR equal to Vs VR by X angle 90 minus delta and minus VR square by X angle 90. Now the real part component by the cosine component and the imaginary part is given by the sinusoidal component. So PR is the real part which is given, which is the active power given by Vs VR by X cos 90 minus delta minus VR squared by X cos 90, and cos 90 turns out to be 0. So this is Vs VR by X sin delta. So this is a general equation for real power transfer in a transmission line. Now QR is given by Vs VR by X sin 90 minus delta minus VR squared by X sin 90, which turns out to be 1. So you will have QR is equal to Vs VR by X cos delta minus VR squared by X. So from this equation you can arrive at two results. The first one is your real power is proportional to sin delta, further it is proportional to delta, and your reactive power is proportional to Vs sin delta minus VR. So the equation is VR by X into Vs sin delta minus VR. So it is proportional to Vs sin delta minus VR. Now, so your real power will be depending on the real power flow between 2 points in a transmission is depending on the angular difference between those 2 points. If you are considering one sending end and one receiving end, the power flow will be depending on the angular difference between these 2 points, and your reactive power will be depending on the voltage drop. This is your sending end voltage and this is a receiving end voltage. So the difference between the magnitudes of this voltage gives you the voltage drop. So your reactive power is depending on the voltage drop between 2 points in that transmission line, and real power depends on the angular difference and reactive power depends on the voltage drop. Okay. Now what happens if you are not taking I conjugate, VI conjugate, and you are going for VI? What happens? What happens if you take VI? Okay. So the issue with VI is that if you take VI, you will get your real power as negative. you will get the value of real power as negative. So in order to bring your real power to a positive value, you are going for VI conjugate. Okay, so you'll have, in order to make that or you are considering that your real power flow is taken as a positive value. So in order to obtain this value, you are going for plus, you are going for VI conjugate. If you go for VI, if you derive, we can derive with VI. So you will get the result, you will get a similar magnitudes but with a reversed sign. So that is only change that you see. So you go for VI conjugate. Okay, so the result that you need to understand from this lecture is your real power flow is dependent on the value of delta, the angular difference, and the reactive power is dependent on the voltage difference, voltage drop, or the voltage difference between 2 points. So that's why if you are trying to improve your reactive power, you can, that reactive power is depending on the value of voltages. Once you supply your reactive power, your voltage levels vary. Okay, and once you vary your active power, that is directly affecting your delta, or when you vary delta, it is affecting your real power. So those are related, and your reactive power and the voltages are related. So these are the two relationships that you need to understand. So we'll continue with this topic, and we'll have further analysis in the upcoming lectures. Thank you.